Hi everyone. So today I'm talking to Matt Hine, Business Line Director at Allegro MicroSystems, and we're going to be discussing next generation current sensor technology. Hi Matt, how are you?
Great. Thank you for having me on today.
Great, no problem at all. So current sensing basically can be done by three methods. That's using a shunt, using a Hall sensor, or using a TMR. What are the particular attributes of each of them?
That's a good question. And we'll take things back to the shunt because that's the obvious starting point.
Sure.
Now, current sensing through shunts has been done for a very, very long time. Obviously, using V equals IR, you stick a resistor in the series of the current, you're generating a voltage, you amplify that, things are good. And there are many applications where using shunts is very useful. For example, low current, low voltage applications. But shunts have some difficulties, which is why we see an emergence of magnetic current sensors on the market. And this is where my products come into play. Now, magnetic current sensors began with Hall-based approaches, and they began because shunts have fundamental limitations. If you need a faster shunt, you start to run into a lot of parasitic problems. If you need a lower power shunt, you need to gain up the signal more. So higher currents is a difficulty. If you need a shunt that's operating on an 800 volt bus and needs isolation, well, now you need a whole system around that shunt just to operate across the isolation barrier. Sure. So magnetic current sensing, first of all, with Hall sensors, came out as a solution that solves some of these problems a bit better, where isolation is inherent. The part has isolation built in. It can operate a bit faster. Exactly. There's no touching of the hot line with a magnetic current sensor. You don't need to have all this isolation complexity. It's all just done for you in a simple way. They can operate a bit faster than shunts, and you can really reduce that resistance because when you're doing a magnetic current sensor, you're measuring the magnetic field generated by the wire, the conducting wire. It no longer really matters what the resistance of that wire is, so you can make the resistance lower. So Halls are a very common, magnetic sensor, not just a magnetic current sensor. And they operate, of course, on the Lorentz principle. Of course, you have this basically a resistor sitting in the part, and a current is flowing through the resistor. As a magnetic field is applied to that resistor, it pushes the electrons over to one side. It's kind of it's shuffling them over. It's kind of like if you had a river, and the river is like this resistor with your current flowing, and you just had a big fan and you were blowing the river like across laterally. And what ends up happening is on one side of the river, it's slightly higher than the other. And that's pretty appropriate for Halls because you're generating this millivolts of signal on top of your volts. Mm-hmm. And that's proportional to magnetic field. So then with all the fun signal chain technologies that we have, we take those millivolts, we amplify them, we remove the offset, and we give a voltage that's proportional to the magnetic field for a current sensor, the current. And so that's a technology that's been around for a very long time. And with some of the newer advents in clean energy and with silicon carbide and GaN coming in, some of the downsides of Halls have been coming up, where now the question for many people is, okay, the Halls are nice, they give me isolation, but they're not really fast enough. And they're kind of noisy because you're gaining up this really tiny signal. And so newer approaches to how do you sense the magnetic field have been developed. And TMR is one of these approaches that is now coming up as a cool technology. And so TMR is fundamentally very different than a Hall sensor. So a TMR is actually quantum mechanics in action, which is really interesting to say. You actually have a component where the resistance of the component is based on the magnetic field, simply because the magnetic field alignment controls how much quantum tunneling happens through a barrier. So the component operating is actually entertaining because the fact that the resistance changes is just simply an indication that classical physics is not correct, because there's inside a quantum dot, these little TMR magnetic tunnel junctions, you have an electrical layer, and an insulating layer in between. But when the magnetic layers are aligned, you get electrons flowing straight through that insulating layer. And that's because of this quantum tunneling effect. And that's why it's called a TMR, tunneling magnetoresistance. And so what's so powerful about this technology is when the magnetic fields are aligned, the resistance is very, very low. And when the magnetic fields are not aligned, it's very, very high. And so we get a ratio of that resistance that can go from close to 0 to 100% versus the magnetic field. And so this is a signal coming out of the transducer that's orders of magnitude higher than anything we got out of Hall sensors. So that's the basics of the technology. What it ends up allowing is we don't have to apply as much gain to it. We don't need to amplify things up. And it's a lot faster. You're not relying on moving charge carriers across a resistor. It's a quantum tunneling effect that's very, very fast. So the transducer itself can operate at very, very high bandwidths. With this latest product, it's a 10 megahertz current sensor, and the transducer is incredibly fast. Also, because we don't have to gain it up very much, the noise is incredibly low. We get noise numbers coming out of the part that are 4 times lower than other products, even when other products are operating at 10 times lower bandwidth. So it's a significant improvement in the operation of the device when we talk about TMR. So this is the new technology that Allegro is leveraging, not just in current sensors, in other places as well, but in these cool, fast magnetic current sensors.
That's great. So obviously, as you say, this is a totally different approach, and it has the benefits, or plays on the benefits of magnetic sensing in general, but obviously brings this quantum element into it, and obviously that sort of changes things up totally. Because obviously in the past, there were drawbacks of using Hall sensors in terms of their stability, in terms of accuracy, and like you say, you get to higher current. So we've already touched on it a little bit here, but what are the key trends you're seeing in power system design that are pushing this? Because obviously, as you mentioned, wide bandgap technology, that really sort of changes the whole way that power system designs are implemented, because they can go at a lot faster speeds, they can go at higher voltages, etc. So I'm guessing that all these things pretty much favor TMRs greatly then, yeah?
Yeah, and there's a couple of mega trends that we're tracking that have driven us towards more high bandwidth current sensors, and specifically the adoption of TMR. So first of all, as you mentioned, just simply the adoption of wide bandgap semiconductors, silicon carbide and GaN. We'll talk a little bit more about that, but let's just talk about the components themselves. Sure. Those components versus IGBTs and MOSFETs, they operate at much higher switching speeds, but that comes with a little bit of a downside in that they will blow up very quickly in the case of an overcurrent condition. And so silicon carbide's a bit slower, microsecond range. After a microsecond, they may blow up. GaN, there are some GaN components out there that after 100 nanoseconds, they're gone. And so simply adopting these components in modern systems means you need to protect them from surge currents, large currents. And before, you had tens of microseconds to respond and shut down. Now you have down to 100 nanoseconds. Okay. And so that you need a very different approach to protect a component in 100 nanoseconds. So that favors high bandwidth current sensors, especially ones that are isolated in these isolated applications, where you can have something where you're not sending a signal across an isolation barrier and having to reconstruct it and do all those things. The TMR current sensor can give you a response very, very quickly, so you can take action very quickly to protect the system. So that's one quick one. But more broadly on why customers are adopting these wide bandgap, when we look at DC to DC power conversion, especially high voltage DC-DC power conversion, and this spans multiple applications. It spans places like clean energy, solar applications. It spans the chargers in electric vehicles, data center power supplies. All of these applications have places where you're converting a high voltage DC voltage to another high voltage DC voltage or a low DC voltage, and that's an isolated DC-DC stage. These are typically made with a resonant tank converter. And so it's a lot of inductors, a lot of capacitors, and you're creating this resonant waveform that is thrown across an isolation barrier through a transformer and reconstructed on the other side. And so this gives you some challenges because the slower that waveform is switching, the bigger the inductors need to be. If you have a 50 kilohertz resonant tank, it means you got some pretty big inductors and capacitors. Sure. You have a 100 kilohertz, it gets smaller. If you have a 500 kilohertz, it gets smaller. So the faster you can operate this resonant tank, the smaller the circuit gets, the cheaper the components, the big transformers and capacitors get. So there's a lot of cost savings and space savings. If you think about an electric vehicle, your onboard charger, the faster you can operate that resonant tank, the smaller that circuit can be, the lighter it can be. And so you get benefits of cost and weight we're operating. And so this drives the need for fast control. Like, how do you measure a 500 kilohertz, 1 megahertz, 2 megahertz square wave or sine wave operating inside this resonant tank? And you need a current sensor that's not just 500 kilohertz or even 2 megahertz. You generally need a couple of harmonics on top of that. So 5 times or even sometimes 10 times higher bandwidth. And so this drives the need for a lot of these higher bandwidth current sensors, again, vis-a-vis TMR, where we can now measure these signals that are happening inside the resonant tank for high accuracy, high efficiency, so customers can reduce the size of all these really big metal components inside the system. That's point number 2. Point number 3 is related to efficiency. So one of the biggest reasons that, one of the biggest benefits that TMR gives outside of bandwidth is noise. And it's related to bandwidth because typically when you go higher speeds, you pick up more noise. TMR is just natively a better sensor, so there's less noise to pick up. Some systems, especially when we talk about green energy, clean energy, you think about a solar, string inverter, solar microinverter, power converter. These systems typically don't operate at 100% all the time. So if it's a slightly cloudy day, or like if it's, it's dusk, you don't have perfect angle on the solar panel, they're not operating at 100%. Sometimes they're operating at 20%, 25%. But you still want to get as much energy out of that as possible. And the challenge with many classical approaches is at light loads, your noise becomes the dominant factor. And now you're not operating efficiently at light loads anymore because you've got 200 milliamps, 300 milliamps of noise, and you're trying to do that on top of a 1 amp signal. That's not great. So TMR brings in a really, really low noise floor. Even though this new 37100 has a 10 megahertz bandwidth, it's 25 milliamps of noise. And if you low pass filter it, it goes down even lower as the bandwidth goes down. And so it gives the customers the opportunity to operate their system at a wide dynamic range, getting high efficiency at the max load and even down to lighter loads, so they can eke as much energy out as possible.
Okay, so that's interesting. There's a couple of things there. Obviously, let's take it back to the previous point.
Yeah.
Obviously, from a design point of view, if you can reduce the size, as you said, of the magnetics involved, transformers, etc., in a design, you save weight, you save space, and all that. So in particular, I'm thinking, applications like, say, an electric vehicle or an eVTOL. Those are the sort of things you want to get that. You want to have the efficiency as high as possible, and you also want it as lightweight as possible, because the lighter it is, the longer it's going to be able to travel between recharges.
Right.
So that makes perfect sense. And then, as you say, some of these things, especially sort of when we're talking about microgrids and so forth, it isn't going to be at full load all the time. It's going to be, somewhere in between. And like you say, if you've got a low noise floor, you're not sort of, you're not limited by that when things aren't as, when it isn't as sunny, or, the wind's not blowing as hard or anything like that. So that
exactly
makes sense. So yeah, obviously you've touched on some of the reasons why you're going to TMR. Makes sense there. I'm guessing you're having regular conversations with your customers about what they need. So, you've already sort of said, responsiveness is clearly important, because, as you said, with GAN or SiC devices, you've only got a very short amount of time. If something is going wrong, and you need to know about it quickly, because you've only got a very short period to deal with that. So clearly responsiveness is going to be important, as we've already said.
Yes.
Sort of, accuracy and stability are going to be vital. And I know, as already, I guess, as a given, the stronger isolation is really important that TMR gives as well. So when you have the discussions, whether that's with a EV manufacturer or a renewable energy company, these are the sort of things they're talking about then, yeah? Sort of accuracy, stability, faster responsiveness.
Very, very common trends in the market is how do I make my system cheaper? And that ends up being, how do I make my system smaller, more compact? Mm-hmm. How do I minimize components that used to be very large and make them smaller so I can get more power density out of the same area? Very popular trend right now in data centers is, how do I get more power out of the same area? Mm-hmm. And having faster current sensors is one way that they can do that, by reducing the size of all of these transformers and capacitors. As we look at the protection aspect, as I mentioned, if a customer is going to adopt a GaN FET and create a solid state switch out of GaN, they need a very, very fast, isolated, accurate current sensor, so that that GaN component can be run up to its limit, and they get the maximum value out of that component, and safely and accurately shut it down so that it doesn't incur damage. And then on the clean energy side of things, a lot of discussions on how do we minimize the total system cost? How do we maximize that payback period for their end customer?
Yeah. And
part of that is, of course, let's make components cheaper and smaller and all that good stuff. How do we make sure that the light load efficiency is maximized so that we can eke out all that power? Again, going back to that payback period, making sure we get as much power out of it as possible.
Yeah. And
then how do we enable even higher isolation voltages so that we can string more panels on there and get even more energy out of the same system? And so higher isolation trends we see in those markets as well.
Yeah, as you say, with any renewable energy installation, you want the return on investment, you want that to be as quick as possible, because that makes it more attractive to the end user. So that totally makes sense. And as you say, so that's and the more sort of the bigger the scale you can put into that, a higher density you can do, the more money is going to be saved, and so that also ties in with that. I mean, I guess what are the other sort of areas that you're dealing with there? You mentioned obviously renewable energy, we mentioned EVs and stuff like that. Are there any other key markets that you tend to have these conversations and they have similar sort of demands, would you say?
Yeah, I mentioned the AI data center. Server power and data center is a very popular topic right now for various reasons, but that's a place, and I touched on this, but I'll expound on it. Yeah. Power density is a premium there, where before we were talking a 50 kilowatt rack, and now it's a 500 kilowatt rack, or trying to push up to a megawatt rack. The power density requirements are just insane. And to do that, every component is scrutinized in terms of its size and contribution. And so having a component that can result in other components getting smaller, the transformers, the capacitors, means the entire system can scale up in a way that is really, without fast magnetic current sensors, they could not achieve the power densities that are targeted for some of these new AI data center power architectures. So it's a very cool trend that we see in the market, and they're definitely on the forefront of adopting things like GaN, things like the fastest current sensors out there, because they are under the gun, so to speak. Yeah. So that they can get these power densities up, and they can deliver enough power to the GPUs and the cards.
Because they're really pushing the limits, as you
say. They're really pushing the limits, exactly.
And the more they can fit onto each shelf and each rack, the better for them, because then that's okay. So that makes sense. So that's another key market, and obviously that's, as you say, at the moment, that is clearly very front and center.
We also have discussions, interestingly enough, with classical motor drive customers. And so motor drive is not an application where customers really need to go fast. The motor is a giant inductor. And so it's not like you're going to have a 1 megahertz switching frequency in a motor. But what's really attractive about this TMR current sensor, the 37100, to motor drive customers is actually the noise level. Is because if you're trying to operate a very tight control loop on a servo motor, if your current sensor has a lot of noise, it causes jitter in the motor, and it kind of goes back and forth and causes some instability in the control loop. So having a very low noise current sensor is something that's actually attractive to motor drive customers who are designing VFDs or very high efficiency servo drives, because it allows them to operate more efficiently.
That makes sense, because obviously there's a big push at the moment. Obviously, one of the biggest users of electricity globally are motors. And obviously, if you're a motor drive manufacturer or an operator, then you need to try and keep that down as much as possible. And as you say, that responsiveness, if that can improve the control loop, then you're going to have more efficiency, because you're going to have less issues with jitter and so forth. And that's going to mean the whole thing runs smoother. And so
there's energy to be saved there.
Yeah. Okay. So that can make a big difference in terms of how those things operate efficiently. Okay, that's
exactly.
Great. And you've touched very briefly on your latest extreme sense TMR. So obviously this is the culmination of a lot of the discussions you've had with these customers and the needs in the market. So maybe you could just give me a few more details about that product.
Yeah, so the ACS37100 TMR current sensor, we've designed this product to really showcase what we can do with this Extreme Sense technology. And Extreme Sense is a TMR technology that Allegro has the capability to deposit directly onto our wafers. So in other places where you see TMR adopted in other types of applications, often that's a multi-chip solution where there's some difficulties in integration because the TMR is its own die, and then you've got your control die, and they both have to be co-packaged. Yeah. But the solution that we've brought is single chip, monolithic, basically looks and feels the same as any other current sensor that we've released. So very simple to use. There's not anything customer has to program or figure out how to do. It's all built in, ready to go. And so this component, we've really pushed the boundary on what we can do with magnetic sensing, leveraging the TMR. So that the main spec that we have that we talk about is the bandwidth. It's a 10 megahertz current sensor. And as part of that, it has a 15 nanosecond response time. And so it gives you a very, very fast response. On top of that, it's your standard analog current sensor, of course. It gives you a voltage that's proportional to the current vis-a-vis the magnetic field measured. This device is in a isolated package, and so it has a over 500 volt RMS reinforced rating, which is 1,000 volt basic, depending on what kind of system you apply. Mm-hmm. And in this package, it actually has 8 millimeters of creepage and clearance, which is very commonly used for 400 volt or 800 volt battery or supply applications. Now, the part outside of just the standard, it's an analog output proportional to the magnetic field, we threw in a couple of extra features which are very common in these sorts of products. It has a voltage reference that customers like to use to give a more accurate measurement of the signal. They can do a pseudo differential measurement of the output and the VREF. In addition, the part has an adjustable overcurrent fault, which is really useful in a fast current sensor. Because sometimes the slowest part of the customer's overall response is the digitization of the analog output and then taking a response in the microcontroller. But this part also has an adjustable fault threshold. It's an open drain output, and you can adjust the actual threshold, what current the fault trips at, on an analog pin on the part. So it has a hardware fault feature that responds within 100 nanoseconds that tells you the current has exceeded a level in very quickly, and you can take a much quicker action that way if you want to. So that's another feature that's available on this product.
Great. So that's available as of now then, basically. I think you released that sort of...
It's available today.
Okay, so that's cool. I mean, we've already sort of touched on most of the applications. Are there any other ones that you'd sort of want to mention? We've obviously touched data centers, EVs, and renewable energy, but are there other ones and motor drives as well? Are there any other ones that are likely to be of value?
As we look forward into emerging applications, we're very interested to leverage this sort of TMR technology in robotics, and not necessarily, as a first step, but as we look at the kind of noise levels that TMR can enable. We're looking at how do we leverage this technology and use this part as an example to showcase what this technology can do, really to allow customers to miniaturize robotics actuators, either in large joints or small joints or anywhere that can be used. Because obviously size comes at a premium there, and performance is also a premium. And so we're excited in the future as we look forward where this technology can be applied, where we can use it.
That's interesting, though, because as you say, obviously robotics, there's only limited space in them. A lot of them are using, as you just mentioned, for joints now. They're using wide bandgap technology for the joints of appendages and so forth. So obviously you want to make use of wide bandgap, but you've got to do it in a compact, responsive way.
Small and fast. Small and fast and accurate and everything. And low loss as well, because there's not a lot of space to dissipate power on those boards. And so that's an area where TMR technology really can enable us to make effective current sensors in those markets where legacy current sensing solutions may cause some problems. So I think the future is very bright.
Okay, so that's interesting. But as you say, robotics, obviously, a lot more interest at the moment in humanoid robotics over the last year or so, and people like Elon Musk making a big point about it recently and so forth. And I guess, like you say, you've got to have those compact, fast, responsive sort of solutions there. I mean, in terms, final thought is on in terms of where you can take the technology actually at the device level. How far can you push this now in terms of speed, in terms of higher voltages and so forth? And I mean, do the laws of physics come in at some point and say it's going to be harder to keep on, moving forward?
The great thing about TMR, for me, as someone who's running a development team for current sensors, TMR kind of removes all barriers to the rest of the signal chain. And it really removes all the excuses where before you're just doing so much on a Hall element that the rest of your signal chain really doesn't need to be that good. Like there's a lot of efficiencies and things. We've been optimizing how to make a Hall signal chain for over 20 years at Allegro. So we know how to do it really well. Switching to TMR is interesting because now you have a transducer that's several orders of magnitude better, higher signal to noise ratio, faster. And that puts the onus back on the rest of the signal chain to kind of catch up and be able to respond quickly and have all that stuff built in. So the capability of the Extreme Sense TMR is very high. And we now get the opportunity to develop new solutions that can get full use out of that TMR. And so the future is very bright there.
Yeah. And I guess moving forward then is trying to get the overall solution as small as possible, get the responsiveness quicker. I guess trying to get the cost down overall, is size and cost, getting that further and further down are the key things there.
There are huge trends in both miniaturization and making solutions that are smaller, lower loss, more efficient, as well as solutions for just simply higher voltage capability, higher power density. And both of those trends actually tie into the TMR technology quite well because it gives me strengths on both ends. On the low end, for the miniaturization capability that TMR allows us, and on the high end, for the high isolation that TMR can enable us.
That's great. Matt, it's been really interesting. Thank you very much for informing me so much more about TMRs and what the future holds for them. It's been a pleasure. Thank you.
Thank you very much. Appreciate it.